If you want to have even stronger, more techno kind of stuff, you can actually use a wave shaper, because a wave shaper will really make a very drastic, dramatic effect. Let's see, another cable. So if I feed the output of this filter into the input of a wave shaper, and we listen to the output of the wave shaper, let's see. Then I can immediately explain a little bit about this wave shaper. This wave shaper is basically technically it is frequency modulation. It's linear frequency modulation. Only the so-called carrier oscillator is not present. Instead, it produces frequency modulation on a 0 Hertz signal. So a signal that has no pitch. Sounds a bit crazy, actually is a bit crazy, but it is a quite interesting situation, because if you look at all the math of frequency modulation, then the results are always defined by the pitches of the modulator and the carrier. But if you would reduce the pitch of the carrier to 0 Hertz, then suddenly whatever you do will always inherit the basic pitch of the modulator. So you will create harmonics, because FM will, but always in the pitch of the modulator, which is great, because then we can use anything as a modulator and will not get enharmonic signals. So actually that is what happens here. I can set the input level of the wave shaper, and I also have a crossfader here between the clean input signal and the wave-shaped signal. If I crossfade to the wave-shaped signal and the wave-shape level is off, we hear the 0 Hertz signal, which is silent. So you hear nothing. But now when I start to open this, the signal starts to appear. Then it starts to sort of fold around. And we create a lot of harmonics. You shouldn't overdo it, just keep it creamy, as they say. But you can still sort of set the amount of harmonics with a mixer that you want. Okay. Any questions?
Do you think you could show us how that works on the oscilloscope with maybe like a sine wave or something? Just so
Okay. Yeah, good idea. So basically, here we have our sine wave, and if I now crossfade to the output of the wave shaper without the wave shaper having an input, you see that it just drops to 0. Now I start to open the input to the wave shaper. First, you have to sort of imagine that if you have 0 hertz, you start to modulate around 0 hertz. So if you just have a bit of modulation depth, it goes between maybe plus 100 and minus 100 hertz. And minus 100 hertz is the same as plus 100 hertz, but with the phase inversed. So basically, that's why it works with a 0 hertz frequency, because the plus and the minus that it will generate will basically transform into amplitude levels. So, but you see that now we're moving more towards a kind of a square wave kind of signal, because we now basically push it a bit to the positive, and then we go a little bit back, go back to that positive point, then push it to the negative, go a little bit back, then back to that point again, push it to the negative. And that way, if I keep on opening it, you will see that the waveform sort of folds until this waveform. There's a couple of interesting tricks that we can do, because we can manipulate the input to the wave shaper, and I have a knob here that will sort of make the input asymmetric, which sort of doubles the pitch. So now if we crossfade back to the clean input signal, you see that we actually create the second harmonic. And we can just set that in any sort of blend that we like. To create more harmonics on that sine wave that we have. And of course, this just, because this is a direct sine wave from this oscillator, the good thing about this 0 Hz FM is that because it is totally symmetric, it doesn't matter what the pitch of the modulator actually is. The waveforms will stay the same if I tune it up or down. And we can get to points where the fundamental totally disappears, which is also a case that you have in FM, linear FM frequency modulation.
Would the wave shaper frequencies be the modulator normally?
That goes into the wave shaper.
Yeah.
Yeah, that's the modulator. So this wave folding, sometimes I call them wave folding wave shapers, you should see as a FM carrier operator that has an input that will act as a modulator. But this carrier FM oscillator is tuned to a pitch of 0 Hz.
Yeah.
And basically is a true 0 oscillator that can also produce negative frequencies.
Right.
And you actually don't use an oscillator for this. It is more like a table lookup method. But that doesn't matter. It follows the math of this specific case.
You couldn't just draw it on the board, could you? And just put the diagram of the carrier in there, the operator.
Yeah, so basically, the idea is that you have a a sine wave
Yeah.
oscillator that it has the ability not only to pitch from 0 hertz upwards to maybe 20 kilohertz, but also from 0 hertz to minus 20 kilohertz, which digital oscillators by default all can do. But for analog oscillators, you actually have to add circuitry to also do that negative part, which has to balance really neatly with the positive parts, and that's why these so-called true zero oscillators in the analog domain are quite expensive and not always work perfectly. Well, digital oscillators by default would be true zero. So this one is tuned to 0 hertz. 0 hertz. Then basically you have your linear FM input, and what you feed in here is basically, so this is your carrier, and this is your modulator. Now, there is a waveform coming out of here that goes positive and negative. And here is basically a signal that comes out that has a frequency spectrum, where in the middle the frequency is 0 hertz. And here, for instance, it's 20 kilohertz. And this is minus 20 kilohertz, which basically is the inverted 20 kilohertz. Now, the moment when this goes positive, it will start to increase the pitch here in that direction. That means that the output level will rise. And when it is at the top, it will be at this point, and then it will go back to this negative level where it is low, and then back again. So basically, if you have this situation where you just only have a so you can imagine that if the amplitude of this signal is 0, yeah, this oscillator is at 0 hertz, which basically means nothing happens. So you have your 0 volt output signal. So then when you just open it slightly, it starts to do this up and back, and that will give you basically that thing. Now, and then why you actually get all these, so now basically you have to see this as a non-linear function, where if you would make a graph, you would have sort of a graph that goes like this, that actually you can draw with these so-called Bessel functions, where you sort of use the input signal as an index to find on the x line, to find a value on the y line, and then if you put that out, you basically get these effects.
But the actual fundamental frequency of that carrier is determined, is the same as the modulating.
Yeah, because whatever happens here will always follow the vibration rate of what comes in.
Yeah.
Because the 0 hertz here will not add anything to that. Yeah, it's not a linear FM workshop here. Because that is something that you can talk about for 3 weeks.
Yeah.
I really should first explain what that is to really explain how it works. But basically, this is what it is. And the trick is that because you can actually do that with a wavetable, with a lookup table instead of an oscillator, in the analog domain, you don't use an oscillator, you actually create sort of like a lookup table. And well, you can find schematics on the internet on how you do it with diodes and stuff and things and blah, 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 blah. So But it's more a bit about how you work with these wave shapers, because one of the things that I like is to sort of be able to crossfade between the in and the output, so you can actually define how much. And this is actually also under, more or less under voltage control, because we have a VCA on the input, which actually is a bipolar VCA, so a ring modulator. So you can actually also use it as a ring modulator. So if I take, for instance, this positive only triangle output of this second LFO that we have here, and I put this into the VCA modulation input, we can have voltage control over the modulation depth.
So that's crossfading between the original signal and the shaped signal?
Now that is actually defining the depth, because this is our original input signal, and now I crossfade to the wave-shaped signal, but I voltage control the input to the wave shaper.
So it's just the
After
amount
the crossfader.
of level that's coming
Yeah.
into the module,
Yeah.
into the shaper.
So you can make it more subtle. Another thing that you can do, you can also decide not to use this VCA that is in front of the wave shaper, and you can take a VCA output of an oscillator directly. Now the output is closed, so I can put it into the super sensitive input of the wave shaper, and now if I open here, I can also basically produce wave shaping, and then use this LFO here to control the VCA modulation that I have here, and do it in different ways, or use another LFO. And that way, and now this knob doesn't do anything anymore because this controls the VCA. This still controls the mix, but that is the mix between the output of the shaper and the input of the VCA. But I can also switch this to the point before the shaper, but you hear now that the signal level also depends on the output level of the oscillator, so many times that's not really that useful, but maybe sometimes it can be.
Sorry, Rob, the switch is controlling the crossfade,
Yeah, because
changing the nature.
yeah, because basically this shaper mix crossfades between the switch, it's written here, the switch, and the wet output signal of the wave shaper. And so this switch defines whether this switch points to the input pre-VCA, this one, totally off. So now this becomes like a volume knob for the wave shaper signal only, or pre-shaper, where basically you have this signal but slightly less volume, because now I have to tame down the volume here to control the wave shaper. Okay, you have to play with that, and then it's about the behavior, and then very soon you grasp the behavior and it becomes clear. Explaining it makes it sound very complicated, but in reality actually it isn't. It's just do and listen, use your ears. So then I can sort of a bit manipulate the sound, because as you see, it's a very, I only have to give it a very little bit of volume before it already starts to do something. Then we have two options. So we can add an asymmetric thing to the signal, and we can add saturation to the signal, which basically means that if you just have a little bit of signal, you can sort of change it from like a sine to sort of like a square. But then you have one thing, that if the signal goes off, it kicks in very quickly. So you get a bit this effect, which you don't have if you don't have that. So, but then there is one other thing I have to say about this, and that is, imagine that this is not a sine wave, but it is a square wave. We use a square wave instead. Then we have a slightly nasty situation, because basically the effect of the wave shaping is produced by the angle of the waveform. And if this angle is sort of like 45 degrees or sort of like constantly bending nicely, everything works fine. But with a square wave, actually the angle is perfectly 90%. And that doesn't mean that the output sort of smoothly fades from positive to negative, but it sort of jumps. And that basically means that if we use a square wave signal, let's say we use I go back to my VCA input. I take a square wave signal from here. Then you see, it behaves in a different way. Actually, the square wave signal is probably not, the positive voltage is slightly different from the negative voltage. So you see that we have a slight thing, but it doesn't really sound that dramatic as what you would do with a thing. But then actually this asymmetric thing can sort of change that, because if you use that asymmetric thing, you see that I can actually sort of change that square wave into a sawtooth wave kind of thing. And meaning that you will also have the even numbered harmonics present instead of only the odd numbered. So that's one of the reasons why this symmetry shaper is there, because that will severely help with the wave shaper. And of course, the overdrive doesn't really do a lot here. Okay. So normally you would use a wave shaper with waveforms that do not have 90-degree transient flanks, as we say in the Netherlands, or edges. So, but sort of angles, slopes that gradually move up and down 45 degrees or bend a bit, then it works much better. And basically the original idea is to use it with sine waves. But then if you use a filter with a high resonance, that sort of creates like a sine wave in your at that resonant frequency. So that's why these wave shapers work very well with filter sweeping on high resonances, etc.